Now it is visible.
Yes, sir.
Okay, ma. I think we are in the last question, part B, 19th question. What is the external treatment of the water? Explain any one of the method with a neat diagram and write its advantages and disadvantages. Already yesterday I shared the diagram of the external treatment of the water. The example of the external treatment water is the ion exchange process, and it contains the two columns. One is the cation exchanger column and second one is the anion exchanger column. By using cation exchanger column, we remove the cationic hardness from the sample of the hot water, like calcium plus 2 ions and magnesium plus 2 ions, whereas anion exchanger column is used to remove the anionic hardness from the sample of the hard water, like chlorides, sulfates, carbonates, bicarbonates, nitrates, etc. Okay, and after that we see by completion of the purification of the hard water up to 1000 to or 2000 ml, the resin capacity should be lost. So that resin is called the exhausted resin. At that moment, the resin is need to undergo regeneration process. So the cation exchange resin is regenerated by the dilute hydrochloric acid, and anion exchange resin is regenerated by the dilute sodium hydroxide. Then only to get a refresh a cation exchange resin and anion exchange resin. Further, it will be the process should be continuous. And we see advantages and disadvantages. Out of the previous methods like Gunsperm process, zeolite process, the ion exchange method is the best process. Why? Because it can remove the both cations and anions. That means cationic hardness and anionic hardness. And it should be purified the acidic solution and alkaline containing the water. And at the same time, the hardness of the water almost all reduces to 0 to 2 ppm, 0 to 2 ppm. So that are the advantages of the ion exchange process. And coming to the disadvantages, so disadvantages are mainly the cost of the equipment is high, because we use the both cation exchanger and anion exchanger. The resin cost is very high. It enhances the total cost of the equipment. And second one is the process, ion exchange process applicable to remove the ionizable impurities but not non-ionizable impurities, especially for example if you use the turbid water. So turbid water cannot be removed by the ion exchange process. So that are the disadvantages of a ion exchange process. Okay, ma? Okay, now all of you understood the part B questions, amma?
Yes, sir.
Okay, ma. Then move to part C. Part C questions mainly involves the problem solving and critical thinking, especially reasoning questions. So now we see first question: why do we add the buffer solution during estimation of hardness of water by EDTA method? By EDTA method. Okay, ma. Anybody know what is the reason why buffer solution is added?
Range.
To maintain constant pH range. Okay, ma. Very good. So how much pH is required for EDTA method?
8 to 10.
8 to 10. Okay, very good. So 8 to 10 means we use the which buffer? Acidic, neutral, basic.
Basic, sir.
Yes, very good. Basic buffer. Basic buffer is the applicable for the estimation of the hardness of water by EDTA method. So already you know the importance of the buffer. Buffer solution is used to maintain the constant pH of the solution by adding either acid or alkali. By adding either acid or alkali. So that is called the purpose of the buffer solution. In the present titration, the determination of the hardness of the water by EDTA method, mainly the hardness caused salt, which in the which are present in the water like calcium and magnesium salts, forms the complex with the ligand. So that is nothing but a EDTA, ethylene diamine tetraestic acid. So finally the resultant metal EDTA complex is formed. That resultant metal EDTA complex is stable at a pH of 8 to 10. So that's why it is need to maintain the pH 8 to 10. For that purpose, we use the basic buffer solution. Basic buffer solution. And anybody know what is the combination of basic buffer?
Strong acid.
No, ma, no.
Strong base and weak acid, sir.
No. Strong acid and weak base means neutral. But we maintain the pH 8 to 10. So for this condition, basic buffer, we use the weak base and salt of strong acid. Okay ma, weak base plus salt of strong acid. Okay ma, can I give the example for weak base?
H4OH.
Yeah, very good amma. Ammonium hydroxide.
Plus
And salt of strong ammonium
NH4Cl.
chloride, NH4Cl. Okay ma, the combination is ammonium hydroxide plus ammonium chloride, weak base plus salt of strong acid, and the formula is NH4OH plus NH4Cl. So we observe the ammonia is common in both cases, weak base and salt of strong acid. So that's why this buffer is called as ammonical buffer, ammonical buffer solution. Plus okay, and the buffer is called as a ammonical buffer solution. Now the preparation of this buffer is 17.4 grams of the ammonium chloride. 17.4 grams of the ammonium chloride is dissolved in a 142 ml of the ammonium hydroxide solution. 17.4 grams of ammonium chloride is dissolved in a 142 ml of the ammonium hydroxide solution. Then the resultant solution is make up to 250 ml volumetric flask. 250 ml volumetric flask. So that is the preparation of a buffer solution. Okay, now coming to the point, the first reason is to maintain the pH 8 to 10, and at that pH the resultant metal DTA complex is stable. So that is the first reason. And the second reason is to show the color change of the indicator. To show the color change of the indicator. Okay, ma, anybody remember what is the indicator used for hardness of water?
EBT.
EBT. Very good, amma. What is the full form of EBT?
Erythrom black tea.
Erythrom black tea. And what is the color change?
Wine red to
Wine red to blue.
Okay, ma, very good. Wine red to blue color. So wine red color is forms when metal forms complex with the indicator. When metal forms the complex with the indicator. So that means initially by taking the water sample like hard water, and it is mixed with the indicator EBT. So the metal ions present in the water solution forms the complex indicator to show the color wine red. Then further it is titrated with EDTA for the determination of the hardness of the water. Then what happens? EDTA replaces the indicator from the metal and to form a stable complex like metal EDTA, and leave the free indicator, so that is the blue color. So that's why the color changes from wine red to blue. And the purpose of EBT indicator to show the required color change from wine red to blue based on the pH range 8 to 10. So this is the second reason. Okay ma, so that's why we add the ammonical buffer solution for the estimation of hardness of the water by EDTA method. Okay ma. The first reason is to maintain constant pH 8 to 10 for the purpose of to form stable complex metal EDTA complex. And the second reason is to maintain pH 10 because to show the color change of the indicator EBT from wine red to blue color, from wine red to blue color. Okay ma. Next, what happens when temporary hot water is boiled? Give reactions. What happens when temporary hot water is boiled? Give reactions. Okay ma, I think all of you know temporary hardness is removed by which process?
Boiling of H2.
Boiling of that resultant water, hard water. Okay ma, what are the salts causes the temporary hardness?
Carbonates, bicarbonates.
Of
hydroxides.
Calcium
okay.
and magnesium.
Of calcium,
Calcium and magnesium.
Magnesium. Okay ma, very good. By taking the examples of like calcium bicarbonate, magnesium bicarbonate are examples of a temporary hardness causes salts. So whenever the calcium bicarbonate is present in the hot water, that hot water boiling takes place. What happens? That calcium bicarbonate dissociates into to give calcium carbonate, water and carbon dioxide. The resultant calcium carbonate is a insoluble precipitate. So that is removed by the filtration process. And carbon dioxide is a gas, it is evaporation takes place. Finally, the resultant formula is water, and it is get used for a domestic and industrial purpose. Whereas, for example, if you can take as magnesium bicarbonate on heating to give a magnesium hydroxide precipitate. Thus, precipitate is also removed by the filtration process. Okay, ma? So this is about the when temporary hard water is boiled and to give a resultant products, that resultant precipitates are removed by the filtration process. Okay, ma? And from third question onwards, there is a problems 3, 4, 5, 6. These 4 problems are under the same model, and 7, 8, 9. These are the based on EDTA titration problems. Okay, ma? So already I explained these problems in offline mode classes. Okay, ma? But anyway, just I revise the one model problem. Okay, so first one, a sample of, okay, the first problem is the third problem. 1 liter of the water sample collected from a water source in Telangana has shown the following analysis. Magnesium bicarbonate is 14.6 milligrams, magnesium sulfate is 12 milligrams, calcium bicarbonate is 16.2 milligrams, calcium chloride is 22.2 milligrams, and magnesium chloride is 9.5 milligrams, and organic impurities are 100 milligrams. Calculate temporary and permanent hardness in a degree range. Okay, ma? They are giving the some of the salts, and they calculate the they want to calculate the temporary and permanent hardness. Okay, ma? So first of all, out of giving salts, which salts causes the temporary hardness, ma?
Bicarbonates and carbonates.
Okay, ma. Now in the given salts, magnesium bicarbonate, calcium bicarbonate causes the temporary hardness, and which salts causes the permanent hardness, ma?
Sulfates, chlorides.
Sulfate.
Okay, ma. So in the given problem, magnesium sulfate is there, calcium chloride and magnesium chloride. Okay, ma. Totally 3 plus 2, 5 salts, ma. 3 salts causes the permanent hardness, 2 salts causes the temporary hardness. And what about organic impurities, ma?
They don't show any effect on the hardness.
They don't cause any type of the hardness. That's why to leave that quantity organic impurity. So we consider the first 5 salts. That means magnesium bicarbonate, calcium bicarbonate for temporary hardness, and magnesium sulfate, calcium chloride, magnesium chloride for permanent hardness. Now these salts are present in the units, like for example, magnesium sulfate is present in 12 milligrams. 12 milligrams. So this milligram quantity is converted into a ppm. So that is called the expression of the hardness in terms of equivalence of CaCO3. Expression of hardness in terms of equivalence of CaCO3. Okay, ma? And the formula is amount of the hardness producing the substance by molecular weight of the substance into 100. Amount of the hardness producing the substance by molecular weight of the hardness producing the substance. I again rejoin. Okay, ma? All of you watch my screen, ma? Am all of you audible my voice?
Yes, sir.
Okay, ma. And watch my screen.
Yes, sir.
Yes, sir.
Okay, ma. Okay. So now the topic is the given contents magnesium sulfate is present in the milligrams quantity. So that is converted into a ppm, parts per million. So for the purpose, we use the formula expression of the hardness in terms of CaCO3, expression of the hardness of the water in terms of calcium carbonate. Okay, ma? So the formula is the amount of the hardness produced in the substance substance by mass of the hardness producing the substance. Nothing but a molecular weight of the hardness producing the substance into 100. Okay, ma? So always the hardness is expressed in terms of equivalence of CaCO3. In terms of equivalence of CaCO3. Okay, ma? Anybody tell me why the hardness is always expressed in terms of CaCO3? Is there any reasons?
Sir, its molecular weight is 100, sir.
Okay, ma, very good. And second reason?
It is most undissolvable salt, sir.
Okay, it is most insoluble salt compared to the remaining hardness causal salts like calcium bicarbonate, magnesium chloride, calcium chloride. Out of all, one and only calcium carbonate is the most insoluble salt. So that's why hardness is always expressed in terms of calcium carbonate. Okay, ma? So by using that formula, these milligrams quantities are converted into a parts per million. Okay, ma? After that, conversion of parts per million, then we add the temporary hardness causal salts ppm quantities. After that, we see the permanent hardness quantities within the ppms. So by the combination of temporary hardness ppm quantities and permanent hardness ppm quantities to get a total hardness. Now that is the hardness of the water within ppm. But in problem, they ask about the degree French. Now we know the interconversion of hardness of the units of the water. So what is the relationship between ppm and degree French, amma? Emma, what is the relationship between ppm and degree French?
1 ppm equals to 0.1 degree French degree.
0.1
1.
0.1 French degree. Okay, amma? So that is the relationship between the hardness of the water within the ppm and the degree French. So 1 ppm is equal to 1 milligram per liter is equal to 0.07 Clark degree is equal to 0.1 French degree. 1 ppm is equal to 1 milligram per liter is equal to 0.07 Clark degree is equal to 0.1 French degree. Okay, ma? So that the relationship between finally we got the hardness of the water within the ppm level, and that is converted into a French degree. Okay, ma? So the multiplication factor is equal to 0.1. Okay, ma? And next problem, this is also coming to the under the same model. So in this problem, a sample of the hard water containing the followed dissolved salts like magnesium bicarbonate is 14.6 and calcium bicarbonate 16.2, calcium chloride 111 milligrams, calcium sulfate 1.36, silica 40 milligrams, turbidity 10 milligrams. Now they ask the calculated temporary, permanent and total hardness of the water in ppm, degree Clark and degree French. So now they ask the hardness of the water like a temporary, permanent and total in the 3 units, both ppm, Clark degree and French degree. Okay, ma? Now they give the so many salts, but out of all salts, which salts causes the temporary hardness, amma?
Bicarbonate and carbonate.
Magnesium bicarbonate and calcium bicarbonate. And what are the salts causes the permanent hardness, amma? See the problem, amma.
CaCl2, CaSO4.
Yes, very good. Calcium chloride and calcium sulfate. What about silica and turbidity, amma?
They don't cause any
They
hardness.
don't cause any.
Okay, ma, leave that quantity, silica and turbidity. So consider only 4 salts, magnesium bicarbonate, calcium bicarbonate causes the temporary hardness, and calcium chloride, calcium sulfate causes the permanent hardness. Now these quantities, all are these present in the milligrams per liter, milligrams mgs. Now they are converted into a ppm, parts per million, by using the expression of the hardness in terms of equivalence of CaCO3. So now the hardness to get within the ppm level. So that hardness is by the addition of the bicarbonate salts of calcium and magnesium to get temporary, and chlorides and sulfate salts of calcium salts addition to give a permanent hardness. Finally, the total hardness within ppm and permanent hardness within ppm by the addition to give a total hardness by the total hardness. That is the ppm quantity. But they ask the Clark degree and French degree. Now the ppm hardness is converted into a Clark degree and a French degree by using the interconversion of units of hardness of water. Okay, ma? Anybody tell me what is the interconversion of units of hardness?
1 ppm is equal to 0.1 French degree, 0.7 Clark degree, sir.
0.7 or 0.07?
0.07 Clark degree.
Okay, ma. 0.07. Okay, ma. So 1 ppm is equal to 0.07 Clark degree is equal to 0.1 French degree. Next, a sixth problem is also same category. Now they ask the calculate temporary and permanent hardness of a water sample which contains 6.8 milligrams of calcium sulfate and 33 milligrams of calcium chloride, 40 milligrams of magnesium chloride, 24 milligrams of the magnesium sulfate per liter of the water sample, and they give the molar masses also. So this is a special problem. They give the molar masses, that means molar weights of individual atoms for the idea of the students. Calcium 40, magnesium 24 grams, sulfur 32 grams, oxygen 16 grams, chlorine 35 grams. And first of all, observe these salts. Out of all these salts, they want temporary and permanent hardness. Okay, amma, observe these salts. How many salts causes the temporary hardness, amma?
Carbonates and bicarbonates.
Okay, see the problem. In the problem, is there any salts causes the temporary hardness?
No, sir.
No, sir. Only permanent.
No. Why? Because they having the only sulfates and chlorides. So sulfates and chlorides means they cause permanent hardness. So the quantity of the temporary hardness is equal to 0 ppm, and the quantity of permanent hardness coming out from these salts are present in milligrams quantity, and that 4 salts like calcium sulfate, calcium chloride, magnesium chloride, and magnesium sulfate, all these 4 salts given in the milligrams quantity that are converted into a ppm level by using the expression of the hardness in terms of equivalence of CaCO3. Okay, ma? Now anybody tell me what is the formula? Ma, what is the formula? Expression of the hardness in terms of equivalence of CaCO3.
Weight by gram molecular weight into 100.
Weight means amount of the hardness producing the substance by molecular weight of the hardness producing the substance multiplied by 100. Okay, ma? So that is the formula to get the hardness in ppm level. Okay, ma? So and these salts are converted into a ppm level by using that expression of the hardness in terms of equivalence of CaCO3 formula, and finally by the addition of that ppm levels of each individual salts to get a permanent hardness, and there is no salts causes the temporary hardness as per the problem. Okay, ma? So this is the 6th question, and coming to the 7th question. So from 7th question onwards the model is changed, but anyway I already explained all these problems in offline mode. Again I revise. So the 7th problem and 8th problem, 9th problem, these 3 problems are comes under category of the titration with EDTA. All these 3 problems are under the same model, the only numericals are changed. Now see the 7th problem for model. A sample of the water 100 ml required 12.6 ml of 0.02 molar EDTA solution with EBT as indicator and 8.4 ml of 0.02 molar EDTA for the same volume of the water after removing the carbonate hardness. Calculate total permanent hardness in terms of calcium carbonate equivalence. In terms of calcium carbonate equivalence. A sample of the water 100 ml required for 12.6 ml of 0.02 molar EDTA solution with EBT as indicator and 8.4 ml of 0.02 molar EDTA for the same volume of the water after removing the carbonate hardness. So the first one, initially they take the 100 ml of the water, but 12.6 ml of EDTA consumed for the titration for first one. But in the second titration, they consumed only 8.4 ml, 8.4 ml of 0.02 molar EDTA. Why? Because after removing the carbonate hardness. Why? Because after the removal of carbonate hardness means which hardness? Temporary or permanent?
Temporary.
So temporary. Generally, you know about that. Temporary hardness is removed by the boiling process. So that's why in the second titration, they take the boiled water. Boiled water means temporary hardness is removed. So carbonate hardness is removed. Okay, ma. So that's why the EDTA consumed volume will be reduced. Initially 12.6 and in the second titration 8.4 ml. In the second titration 8.4 ml. Okay, ma. Now I share the solution. Emma, all of you visible the solution, Amma?
Yes, sir.
Okay, Amma. So this is the problem, and already I shared this material to you here. Emma, already you shared the material, Amma, to our students.
Yes, sir.
Okay, Amma. So this is the solution for the fifth problem, and by using the formula M1V1 is equal to M2V2. So this is the determination of the molarity formula while titration takes place. Okay, so initially for they gave 100 ml of the sample required for 12.6 ml of 0.02 molar EDTA. So now left side taken as a water sample and right side is taken as EDTA, ethylene diamine tetraesteric acid. So from left side you don't know the molarity, so that's why the formula becomes M1 is equal to M2V2 by M1. M1 is equal to M2V2 by M1. Now substitute these values. For right side EDT is considered, so the molarity is 0.02 and volume required 12.6 and volume of the water V1 is equal to 100. To get total molarity 0.00252 molar. And for second titration, as per the problem, for 100 ml of the sample, they require 8.4 ml of the 0.02 molar EDTA. Now again use the formula M3V3 is equal to M2V2. From left side you consider the water sample and right side you consider EDTA. And again you don't know the formula of the M3 of the water. So the formula becomes M3 is equal to M2V2 by V3. So M2 is equal to EDTA molarity for second titration, that is 0.02 molar, and volume is equal to 8.4 and divided by volume of the water 100. Again you get a 0.00168 molarity. So initially the molarity represents the total hardness of the water, total hard water molarity. And in the second case, already temporary hardness is removed. That means carbonate hardness is removed. It represents a temporary hardness molarity. Now calculate with the help of molarities the hardness of the water within the ppm levels. So by taking molarity m1, that is multiplied by 0.00252 into 100 into 1000 into 100 into 1000. 100 for the molecular weight of the CaCO3, and to calculate the hardness of the water per liter, so that's why it is multiplied by 1000. Finally to got 252 ppm. And for permanent hardness, that is the second molarity, m3 is equal to 0.00168, and it is again multiplied by 100 into 1000 to get 168 molarity. So this is total hardness molarity 252, and this is for permanent hardness molarity 168 molarity. Now temporary hardness. So generally total hardness is equal to temporary plus permanent. Now we require temporary hardness. The formula becomes temporary hardness is equal to total hardness minus permanent hardness to get 252 minus 168. Finally 84 ppm. Finally 84 ppm. Okay, ma? So this is the required solution for the problem. Okay, ma? So this is the solution for the 7th problem, and 8th problem also same model, and 9th problem also same model. Okay, ma? All of you audible to you?
Yes, sir.
Okay, ma? See the 10th question. What is the main advantage of reverse osmosis process over ion exchange process? So reverse osmosis process is removes only ion exchange process is removes only ionizable impurities, whereas reverse osmosis process removes both ionizable and non-ionizable impurities. Okay, ma? Ion exchange process removes only ionizable impurities, whereas reverse osmosis removes both ionizable and non-ionizable impurities, even like microorganisms and organic chemicals from the water. Okay, so that is the advantage of the reverse osmosis compared to the ion exchange process. Okay, ma? All of you understood the overall questions in question bank, ma? Water technology. Emma, hello.
Yes, sir.
Okay, ma. So from tomorrow onwards, we start the module 3 polymers. Okay, ma? Thank you. Thank you for Thank you for participation in our class. Okay, ma. Now I am leaving.